Thanks for being the math club today. Of course, we got the incomparable Ben Fowler, and he is going to tell us about four color theorem, Kempe's catastrophe. Yeah.
And thank you so much. Yeah, so I want to lead you in by looking at this map of the United States and the way that it's colored. So yeah, when you look for pictures of the map, they're usually colored in a way where when two regions are sharing a border, they use different colors so that you can tell them apart. And this coloring was done using there's four colors: the red, yellow, green, blue. And this could be a kind of tricky thing. Maybe you could try it one time, sit down with a blank map, try to color it in, because you can run into some problems if you're not careful where you color it around and then you're about to color this next region, but it's touching other regions. You've already used up all of your colors, so you're going to have to go, get another marker and add in a color to your yeah, or if you don't want to do that, you might have to backtrack and change up the coloring. And so maybe for this map, it's not so bad. It would be worth trying. Just sit down and it could only take a couple minutes. But maybe for some maps, it could be even more challenging to do that. Like you might get stuck very often, especially if you're trying to limit how many colors you're using. So that could be challenging. There could also be maps where like they just require like 8 colors. Like you just have to if you're color muted, you have to use a lot of color. We'll keep getting stuck otherwise. This map is pretty tame, but you can imagine like taking one of these countries and just like stretching it through, or states, right? And just like stretching it through so it touches more things. And now anything it touches can't be the same color. So, you can imagine a map that's more like swirly and everything's, touching other things. It could be really messy. Yeah, and maybe they could be like, as messy as you want. But actually, it turns out that there's like a worst map that like requires the most colors. Are you ready to see it? It's this one. That's the worst. It turns out actually, yeah, that this map is actually as bad as it gets in terms of how many colors you need. This one used 4, and I just want to point to a couple of places where the difficulty happens. You might think, like intuitively, that the difficulty would be maybe a state like Tennessee that has a lot of neighbors, like a ring of neighbors. But it turns out that having a lot of neighbors isn't always a problem, because you could just have the neighbors alternate colors, so you don't always have to use a lot. So like here's an example. So Iowa has 6 neighbors going around, and they just alternate yellow, green, yellow, green. So when you have an even number of neighbors in a ring, they could just alternate. You could get away with 3 colors there. Nevada is a problem for Nevada because it has 1, 2, 3, 4, 5 neighbors in a ring, and so when you go around the ring, it's like you can go red, green, but then you can't use red and green, so you need a 3rd color just for the ring, and then Nevada touches all of them, so it needs a 4th color. So actually, that is the causing a problem here. Maybe some of the other states are like that too. So generally, it's not so much a problem to have lots of neighbors. You can get 4 should be enough for that. The real issue is like when the neighbors are touching other neighbors. Like the more that like a group of regions are all bordering each other, that's the okay, so that's just like a little intuition of what's going on. But the claim is that no matter the map, 4 colors should be enough. That's the 4 colors. So the 4-color theorem, I have some historical notes. So the 4-color theorem was first posed in 1854. So this was, or at least that's the earliest appearance that we hold. So 1854. Then in 1879, it was Alfred Kempe who released his proof of the 4-color theorem that any map you only need 4 colors. It's wonderful proof by induction. It's short. I found his original paper. It's only 7 pages long, and it probably doesn't need to be. It's very wordy because at the time, like mathematical papers were just like talk to the reader. So it's like just very pretty, but the idea is very simple. It's very nice. It's a by induction. And that proof was published, and it sat for 11 years before in 1890 it was Haywood who discovered there's flaw in reasoning. So the proof is it's a bad proof, but it was 11 years, which is a long time for a proof to sit without anyone catching a mistake. I'm just thinking though. So this was in that was 1879. So at the time, I'm not sure what it meant to publish a math paper. Like if it just goes into record somewhere, who's actually reading it? It's certainly not like today where you can, you put your paper on the archive and like goes to like 1,000 inboxes and people read it and scrutinize it and use it in their work. This time, I'm sure the research wasn't active like that. So it's possible that for those 11 years, it wasn't like the proof was under scrutiny for continuously for those 11 years, but anyone who read it, I guess, was they missed it. So people missed it, and the mistake is subtle, but it's really beautiful. So what I want to do today is share with you Kempe's proof and give you a chance to see if you can spot the mistake. Okay, but before we do that though, we'll start with a little bit of like more introduction. We need to like reformulate the problem in a way that's more easier, or it's going to be easier for us to work with. So let's start there. This map is too large, so I'm just going to use a piece of it. Okay, so the thing about maps is that they have more information in them than we really need for this problem. So all we really care about in the four-color theorem is the regions and which ones are shared borders, because the only condition is that when they share borders, they can have the same color. We just care about which regions are bordering which other regions. We don't care about the relative size of the regions or whether the borders are wiggly. It just matters if they're bordering. So there's a lot of extra information here. We can kind of abstract away just the things we care about and ignore the rest. Here's one way to do that. You can put a dot inside of every region, and then whenever two regions share a boundary, you just draw a line connecting the dots of it to say those two regions are touching. And then you can do that for all of them. So this is what it will look like if you just connect the dots for I'm going to say nodes or vertices, but you could talk about the so you just draw a node in each of the regions, connect the ones that are sharing the boundary, and let's separate this out so you can see that's kind of an abstract version of this map. They don't really look the same, but this has the essential information. It just tells you where are the regions, or what are the regions, and which ones are touching. And so now the problem of coloring the map is a problem of you just have to color the vertices so that whenever two vertices are connected by an edge, they just have different colors. So it's the same problem. It's just a little bit abstracted away, and now we don't have to think about the actual size of the wiggle and things. Okay, so it's the style will look a little bit different, and throughout the talk, I'll mostly use visuals just look like these, but then maybe I'll go back and forth because sometimes you should forget what they represent as we're more familiar with like maps of states and countries and things. Okay, so maybe a little bit of back and forth. Okay, now there's something interesting about this kind of the graph that you get in general from doing this transformation process, which is that in this picture, the lines region are not crossing each other. That's a property in graph theory we call planar graph. So when you do this kind of transformation process, it should be that you can sort of rearrange it. Here it already looks like that, but in a way where the edges, the lines aren't crossing. Crossing lines would be like you wanted to connect these two regions, so you can't really do that. You have to like lift them out of the off the board. So that doesn't happen. So these drawings won't have crossing edges. You won't need there won't be the crossing edges. Okay, and so the reason I bring that up is because we actually know some properties or some like stronger conditions about planar graphs, and we're going to use them. So here I made a generic picture of a planar graph. This is a graph where the edges don't cross each other. And it was Euler who showed that in any planar graph, there will always be a vertex that has. I put it here. So there will always be a vertex that has both 5 neighbors. Here's one that has both 5 neighbors. This one has exactly 5 neighbors. There are actually most of these vertices don't have more than 5 neighbors. This one in the middle is like very popular, but what Euler's saying that they can't all be very popular. So it can't be the case that all of the vertices have 6 or more neighbors. That just can't happen in a planar graph. So there will always be at least one vertex. You find it somewhere that's not so popular, has at most 5 neighbors, 5 or fewer than 10. Okay, so this one has 5. So that's true for all planar graphs. So everything we get from maps when we're doing this kind of conversion is going to have this property, and we're going to rely on this to make the work happen. This is one of the core pieces of the argument. Okay, with me so far, and anything you wanted to ask before we keep going? Okay, yeah.
Is 5 minimal? Like, has it been improved since Euler to like at most 4 neighbors?
Oh, I'm sure that we could draw a planar graph where all of the vertices have like 6 neighbors, and some have 5, but there are no like 4 or fewer. So yeah, probably there could be some pretty crowded graphs where like all of them are super popular, and then the least popular ones are 5s. Yeah, no 4s there. Okay, yeah. Anything else to clarify? Okay, so this fact alone is enough to prove pretty handily that 6 colors is enough for any graph. But let's say that at this point we're beginning the proof. So at some point between now and the end of the talk, I'm going to there's going to be a mistake. It's Kemp's mistake, but I'm going to try to cover for it and be as convincing as possible, even when I'm saying something that's not true. But to make it more fair, let's agree, I'm going to be as honest and genuine as possible for all other details. So I won't also lie about something else early on that could, poison the logical reasoning, and then things can go wrong. So I'll be honest about everything, except for I'm going to try to cover up this one detail, be as convincing as possible. So because of that, this would be good if you're feeling skeptical about anything I say. Please just challenge me on it, because I want to make sure that we're all agreeing. And so if you just are feeling skeptical, maybe I haven't been thoroughly convincing, just let me know. So we can do that. But if we get all the way to the end and you've been convinced by everything I said, that maybe you also fell for the same mistake that Kempe did. Okay, you ready? So let's prove the 6 color theorem. Okay, so the claim is that all maps are 6 colorable, meaning that it's enough to use 6 colors to color the regions so that you don't have the wherever there's a boundary, you have different colors. Okay, and the proof is by induction. And so the way we're going to do the proof by induction is on the number of regions of the graph. So we'll start with a base case, which would be like graphs with one region. Actually, I put more on this slide. So this is actually lots of base cases. But what I wanted to point out was, if you have 6 colors available, think about all the graphs with 6 or fewer regions. You can definitely color them because you have enough colors to just give a different color to every. You can just color them. There's so many colors available that certainly the graphs with 1 region, 2 regions, 3 regions, all of those, 6 colors is enough. Just each region is different, no problem. So that's like 6 base cases, but actually for the proof by induction, we really only need this base case, which is there for 1 region. There's only one region graph, and 6 colors, Okay, so that's the base case. And now for the induction step, this part, so the induction hypothesis will be that all maps with n regions are 6 colors. And then we'll have to prove that all maps with n+1 regions are 6 colorable. that will be the inductive step. So here's how that works. We want to show that graph with n or map with n plus 1 regions is 6 color. So start with a graph with n plus 1 regions, and then let's use the Euler fact that there should be one of these vertices that has the most 5 neighbors. I'm going to pick this one that it does have 5 neighbors, and remove it from the graph. So it also took the edges away because these ones that were touching it are not touching anything. So yeah, okay. So now, or in the map version, this would be like just punching out a hole in the map. So you just delete the land there. So now you have a map with n regions. By the induction hypothesis, 6 colors can color this. So color it with 6 colors. Okay. We don't actually have any control over what the coloring looks like. We just know that it's possible. That's the induction hypothesis. Now, add back the vertex. Just put that land back. Put that country back, or that region. Now, the only thing we have to do is color one region. We're able to color it. Then we've colored the n plus 1. Then we're done. That's the whole argument. So the induction is powerful here because it just turns the problem into you just have to color one vertex. That's nice. Okay, so because it has at most 5 neighbors, like in this case it has 5 neighbors, the worst thing is that all 5 neighbors have five different colors. But we have 6 colors available to us, so we have a spare color. Just color. Use the spare color. In the worst case. Okay. That's the done. Six colors. Suffice. Not so far. You know, in the proofs by induction, there are ways to be misleading with proof by induction. Like sometimes the induction step doesn't actually connect to the base case. Like there are those, all horses are brown. Kind of, you can do faulty proofs by induction. But this one really works because when you have like a graph with 8 vertices, you just use Euler to find one with almost 5 neighbors, pull it out. Now there are 7 regions. That's still more than the number of colors. So there's, again, by Euler, there's going to be another one with at most 5 neighbors. Pull it out. Now you have 6 regions. That's a base case, so we can color it. Then add them back in reverse order. So you add back in the one you removed and color it, and then add back in the one you removed. All right, so you can. So this is a real proof by induction. Yeah, it's going to connect base cases. Okay, yeah. Questions so far? Yeah.
I just had a question about when you remove it, other vertices still stay, right?
That's right. So when we're removing a country, we're just removing or a region. Yeah, we're just removing the one node, and everything else stays. That's right.
So other entities would have different paths. Or does it?
Yes, we're deleting that one vertex and all the edges that are connected to it. Okay, yeah.
This might be really stupid. So suppose node purple on there. Suppose all 5 of the points that it's connected to, all 5 of those points have say like 7 points that they're connected to. Wouldn't that just instantly be a fail case? Or
Yeah, so actually it doesn't matter what happens with the other vertices because the only conditions for coloring this are its immediate neighbors. So when we're picking a color for this vertex, we only need to look at what it's currently touching, which is only those 5 things. So
Yeah, but
this is it's just a local.
yeah, but suppose with blue, like it's connected to 7 other nodes, then
Oh, so your question is what happens to vertices that have more than 6 neighbors?
Yeah.
Yeah, that's not a problem. That was like Tennessee on the map that had lots of neighbors in a ring. And it turns out it's actually not a problem because the colors don't have to be distinct, they can alternate.
no, but like what if all 5 of the nodes that are connected to the white node, what if all 5 of those nodes are connected to 6?
If all 5 have lots of neighbors, yeah, it turns out that having lots of neighbors isn't an issue because those neighbors can repeat the colors.
Oh, got it.
Yeah, so it's kind of a counterintuitive thing that having lots of neighbors isn't really an issue.
Maybe one of the things that you want to mention is when you pull that one out, even if all the rest of them had more than 5 neighbors now, that's still a planar graph and it still has at least one node that now has at most 5 neighbors.
Yes, that's right. So when you're doing the induction nested and going back to back to back, yeah, every time you remove a vertex, what's left is still planar. So Euler's result still 5. There's going to be another vertex that has at most 5, and you can recurse. Yeah, another.
Is it sufficient to say like a fully connected map of n nodes all has a color, like a 6 coloring, and then
Oh, so the question is about what happens if there are n nodes and it's like a fully connected, everything connects to everything. Yeah, so that might not be planar. So it will take a little bit more like arguing that, yeah, 5 nodes all connected to each other. There's no arrangement of that which avoids crossing edges. So those kinds of graphs, which would be a problem for us, actually aren't planar graphs, so they won't. Okay, yeah, we'd have to prove that, but we don't need to because we're using this argument. So by induction, so we don't actually have to, think about how many connections there are.
I missed the planar part.
Okay, okay, yeah, so right. Okay, so that's the argument, and that's where the 6 comes from. The fact that this could have most 5, and then we have 6 gives us a spare color. So that's the simplest. That's the simplest thing we could do. But we didn't even touch the rest of the color. We just had a spare color. So it might make you think that if we worked a little bit harder, we might be able to get that number down to get that. And we can. So next, let's improve this a little bit, and we can do the 500. Okay, so 5 colors. Adding back to the color 5 colors. It's the same proof by induction, and it's the same. There's still base cases, so small graphs. 5 colors is a lot. So half base. And for the induction step, we're in the same argument with assume that n regions can be colored like this. So we take a graph with n+1 regions, use Euler to pick the one with the most 5, pull it out, color the graph with the induction hypothesis, and put it back. And the only thing we have to do is color that one vertex. So the argument is completely the same, and we're just in the case I've just removed the rest of the graph. All we have to do is color that one vertex, and the proof is complete. Okay, but this time we only have 5 colors at our disposal, and in the worst case, all 5 neighbors are using the 5 colors, so we don't have to spare colors. Right. Okay, so we might have to do is some kind of recoloring. We want to recolor the map in a way that frees up a color for the middle. And thing is that recoloring graph is challenging because you might say, what happens if I make that red one blue? Well, what if it has a blue neighbor already? So you can't make it blue because then it's already touching them. So okay, fine, maybe we'll make it blue and then we'll make the blue one red. Well, maybe that blue one has a red neighbor, and so this could be just a general problem. If you're only thinking about recoloring one step at a time, there's always going to be, what if it has a neighbor like that? This could just probably it's totally a headache, right? So, but what Kempe realized is that there's actually a nice way to do this recoloring. You can so you pick 2 colors like red and blue, and you start at this red vertex and just look for all of its blue neighbors. Maybe it's that. And then from those blue neighbors, you look for all of their red neighbors. So maybe like that. And then from the red one, you look for all blue neighbors. Maybe there are more. And you keep doing this. Right? And blue, you look for all red neighbors. You do this exhaustively. So you form this kind of alternating chain of red and blue, kind of exhaustively. So so this chain doesn't touch it. If it touched any more red and blue, it would be part of it. I think this looks a little bit better in a map. So let me just go back quickly to the map representation. This is a nice one here. So if you start at Kansas, and look for the blue, let's do blue-green chain. So okay, so you're starting in Kansas, and then you look for its green neighbors. That's Nebraska, and then from Nebraska you look for the blue neighbors. So that's Wyoming, and then from Wyoming you look for the green neighbors. There are 2, Montana and Utah, but then you look for the blue neighbors, this doesn't have any, but this one does, Nevada, and then green neighbors, California, and then that's, that's all. So you get these like 7 states as a blue-green chain. And what's important here is that because we do this as exhaustively, it means that everything surrounding the chain can't be blue or green. It's going to be from the other colors. Like here, it's all red and yellow surrounding. Right? It's completely encased by red and yellow because if there was any blue or green touching it, it would have become part of that chain. So it's completely protected, surrounded by other colors. And so what that means is we can invert or swap all the blues and greens like this. Happens fast. Okay? And that won't cause any problems because it's surrounded by red and yellow. So that won't make it, the new blues and new greens won't touch other blues and things. Isn't that cool? It's like a really nice idea for recoloring. You just have to find this the biggest chain you can, and then you just can invert the colors. Yeah.
Could you go back to the graphic? Yes, like you have one.
Yeah, I get swapped a few times. So sorry, blue and green is great, but that's the original and that's the swap. So
Yeah, I had a question about when you had the graph up with the 5 peasants.
oh, okay, yeah. So let's go back.
So when at the bottom we have red and blue, if those red and blue are connected.
Oh, okay. You're actually ahead of me. I'm going to address that. So that's a good catch. Yeah. So in the way the picture is right now, we can do that kind of inverted, invert the chain, and then that frees up the red color that we could use. We could use red. Okay, but actually there is one small problem with this argument that you're getting at, which is what happens if that chain is so long that it connects to this blue. Period. So now when you try to do that inverting trick, that red becomes blue, but the blue becomes red, and you actually didn't free up a color, right? Still all 5. And okay, so that's a problem. Okay. But there is an idea here. A question.
What if you try with another pair, let's say yellow and orange?
Oh, great. With these? Yeah. Yeah, okay, so it's possible that the yellow-orange chain will connect with these two.
But then,
So when you invert it, it's yeah.
so you have the green free is not connected to any of the other, right?
Okay, yeah, so this is the insight. So that red-blue chain, oh, by the way, these have been now called Kempe chains after this is Kempe's group. So I'll probably say that. So the red-blue Kempe chain is completely surrounding the green vertex, and it's actually keeping it from these yellow and orange. So I guess if you form the green yellow Kempe chain, we can be certain that it's not going to reach this yellow one. Why? Because in order to escape that chain, well, it would have to make crossing edges, which not in a planar graph, right? Or the only way to get out is to go through one of the vertices, but those vertices are red and blue. So the yellow-green Kempe chain will not have any of those vertices. Yeah, so it's really trapped. So when we invert that chain, we are certain that this stays yellow, and so it actually frees up a color. We lose green. And that's the proof. Yeah, more questions.
Can you go back to the map?
So yes, go back to that. Back to that.
Okay, so before you switch the colors, the green and blue, yeah. So for New Mexico and Utah, the corners not matter.
Oh, I'm so glad you mentioned that because I forgot to point that out when we were first talking about maps. For these, corner touching is okay. And actually, I chose this so that there would be corner touching, and I'm really glad you brought it up because I forgot to. Yeah, corner touching is okay because all we care about is sharing a border, and corner touching don't share a border. So they wouldn't we wouldn't draw an edge between them. Yeah, that's such a very good.
So my follow-up question to that is, so you've got a map like that, can you refine it so the corners don't touch? So a way to read it. I mean, obviously you had a different color scheme before, but I mean, can you avoid that?
Oh, yeah, you could probably just punch a hole where the corner is, make a hole, and then they won't touch anything.
I mean, can you recolor it? So, you know,
Oh, yeah, yeah, I don't, the question is like, if you ever have maps with border touching and you always color it with, you know, the border that meet, you know, all different colors. Yeah, I'm not sure. I mean, that would be a stronger type of color. So probably let's say not no, because that would be required to make strong.
That would just mean an additional connection,
Right.
so.
Yeah, if you just had a short border where that corner is between two of the states,
Yeah,
the other two states would be separated.
yeah. I mean,
But
so
you have another connection.
you're right. Yeah. So now, but if you wanted to avoid both pairs of
Yeah.
corners, not being the same,
Then you have a planar problem.
you have a planar problem. Yeah. So let's not answer it. But so yeah, what I'm saying is maybe you have to have the corner the same color, but I mean,
If you allow the corners to be bordered, you will need, I mean, you can always build a graph, right? And divide it by triangles in the middle. And that will need at least that amount of colors. Because every color is touching, right? Every feature is touching the other ones.
oh yeah, if all the regions are touching each other, then yeah, so then they all need to be different colors. Okay, so I just want to make sure I can reinforce the argument here, because this is like a new idea that's very powerful. The idea was if the red blue chain doesn't connect here, we can invert it in three color. If it does connect like this, then it's isolating the green from yellow. So when we form the green yellow chain, it won't touch, so we can invert that chain. Yeah. Wait, I'm not sure. Yeah. Yeah. Any concerns, just raise them at any point. We can also go back and, just kind of ruminating about it until you have questions. Okay, so that we were able to recall. The idea was the original graph as it was colored during the induction hypothesis. We had to do some modifications, but these Kempe chains are a great tool we can use to do safe recoloring. So, and we just argued how you can recolor the map. Okay, that's 5. We're getting really close to 4. So if you're just holding out, please interrupt. Okay, we can do 4 in a similar fashion. So let's continue. Wait, 4 color. And here's the same kind of induction setup where there's that vertex with most 5 neighbors. We removed it, colored this time with 4 colors, and then put it back. We're looking at it, and it's surrounded by the 4 colors we're using. Now, the worst case is that all 4 colors are represented, so there's no spare. Right? So if all 4 colors are represented, there's a fifth one here. It's going to be a repeat color. It's going to be exactly one repeat in the worst case. So it's like this. I have two blues. If the 2 blues are next to each other, then we can make the kind of Kempe chain argument as before, where we start with red and consider the red-blue Kempe chain. We're trying to do it so that we consider the chains where it's like skipping over one, because we want the chain to go around. So let's do red-blue. So if the red-blue Kempe chain does not connect, we can invert it, and it's 3 up prime. If it does connect, then it's now blocking green from yellow. So actually, let's see the same kind of thing we did before. The green yellow Kempe chain won't connect to this yellow, so we can invert it safely without changing yellow. We free up green. Same kind of. Okay. Now, the other possible arrangement is that the repeat colors of blue could be like 1 apart. It could be separated. And now you can't. Now, when you try to make an argument with like something blue Kempe chains, the problem is that blue is now next to everything. Everything's next to blue, so the Kempe chain might not actually surround. Okay, but red is now apart from, I say, green. So let's consider the red-green Kempe chains. So the usual, if it doesn't connect, we can invert it and we have red in the middle. If it does connect, it isolates blue from yellow. So the blue-yellow Kempe chain in there won't touch this yellow, so we can invert it. But that doesn't solve our problem because that got rid of one blue, but there's another blue. So what can we do? One got rid of one of the blue. Well, how about we do the same thing with the red and yellow chem chain, like this. If the red and yellow chem chain doesn't connect, we can invert it and free up red. And if it does connect, then now it's trying to move this blue from that green, right? So the same thing on the other side. So now this one, the blue-green chem chain, is confined by red-yellow, so it can't escape, and it definitely won't touch this green. So we can invert it, and now we've freed up blue from everywhere. The middle. Done. What? Okay, so that was proof. I finished. We've just proved the four-color theorem. Or have we? So okay, somewhere I made a mistake. Let me start to take care of some questions. Okay, yeah.
What if this last chain that we build with red and yellow have a node with the other chain
If
with the red and green?
oh, like this one?
Yeah.
Oh yeah, it does.
No. What if this red and green and yellow chain share a red node with the red and green chain?
Oh, okay. Yeah, so both of these chains have red in them. Yeah, so maybe they touch, but it's even if they touch, it's this red and yellow is still trapping the blue green side. It really doesn't matter how strong. Yeah.
The original, the original map without any chains. Is that more colorable? Like if it has no chains?
Yeah, if there's no chain, you can invert that one. You can invert that one vertex. Yeah. Chains are the problem, so no chains. Okay, you know what? Maybe I need to drop the act of trying to be intentionally misleading. Yes, yeah, please.
Okay, so what if at the bottom there's red on the left, there's yellow on the right, and then there's red on the right and green on the left. What if red on the right touched yellow on the right? I don't know if you'd be able to do it, but math, that's what I'm thinking about is if you know how some countries like Chad, for instance, they have like this weird kind of like jettison shape that kind of goes around. Like would that cause an issue?
Okay, so the question was about if there's more connections, Yeah, so adding more connections doesn't change our argument because all that matters was that this specific ring is blocking in this piece. So if there are more connections, this is just still blocking in.
Oh, I see, sorry.
Okay, you know what? Actually, so I'm still trying to defend, but I think actually I have to give you a lot more credit because you're totally getting on to what's really the problem. So let maybe start to do the review. The real problem, actually, Andrew is totally onto it. But this is the first time that we've done a proof where we considered multiple types of chem chains at once. And actually, what's happening is that both of these chem chains have a common color, it's red. So Peter's saying there is actually a potential for these chem chains to interact. They can pass through each other. They can get tangled. And it turns out that actually that can be used to make this not work. Can I tell you how?
Oh, yeah, because my first question is because I was thinking, what about, you see that red one that is connected to three greens?
Yeah.
Yeah, what if that red one was connected to the blue one, to the yellow one, that is just near it?
Over here.
Yeah. And at the same time, that red one was connected to the yellow one in the other chem chain.
Yeah,
and
okay.
that would not make some
No,
stuff.
you're totally onto it. So there could be an issue where this can sort of escape via the other red yellow green. Yeah, I want to show you what that looks like because it's a little hard to picture. this picture is intentionally misleading. I mean, it's kind of your intuition that the two chains are just going to be some kind of blobs that go around and connect back up, but they don't have to look like this. So this is kind of a case where the picture is not as general as we thought it was. We thought we were covering our bases, but yeah, things can get a little messy. And so here's one way to do it. It would go like this. Before, the red-green Kempe chain went around this way, but in this version, we actually, to make a counterexample, only need 3 more regions to have. So we can make this pretty simple. And this time, the red-green Kempe chain will go around to the left. That's not totally a problem because of what this Kempe chain was doing for us in proof is that it was isolating that blue from that yellow, and it still does that no matter which side we draw it on. So the side you draw it on isn't a problem. Our argument would still work if it agrees. But then we'll do the red-yellow Kempe chain on the other side as well, so it's on the wrong side, and they're intersecting, so they're sharing a vertex. So they're going the wrong way. They're also crossing over each other, which is that's going to be the problem. Okay, so it is true that now it's getting a lot harder to look at, but it is true that the red-green Kempe chain is blocking that blue from that yellow, and the red-yellow one is blocking that blue from that green. The way it was, in our. Now, what we did in the proof is we considered those 2 types of Kempe chains off of the blue and inverted them both. But it was for this one, it was the blue-yellow Kempe chain. But look, now that the chains are crossing, there's a yellow pretty close by, right? There's an accessible one. So maybe that blue-yellow Kempe chain goes through that yellow. And maybe this blue-green Kempe chain goes through that green. So that those chains can use the other side's Kempe chain border. Okay, so this is how they're going to escape. Okay, and then to make this work out, we need a lot more connections. So just add more connections. Connections make it harder to color, right? So to make it as hard as possible, just have every region touches a lot of other things. Just to make it really hard to color. Okay, now let's try to repeat Kemp's argument, which was to first this blue-yellow Kempe chain is not going to reach this yellow. That's still true because of the chain going the block. So we can safely invert this blue-yellow Kempe chain without so if it's not connected, that's still true. Okay. But the problem is that puts a blue over there, and now this blue-green Kempe chain, look, it goes blue, green, blue, green. The blue-green Kempe chain here actually makes it around and is able to connect it to this one. So it used to be the case that it was blocked out, but after that one inversion, we've actually made a path for it to reach. Isn't that awesome? Yeah. So this blue-green Kempe chain escapes and makes it around to the other side. So now if we try to invert the blue-green Kempe chain, like the argument went, it would turn this blue, and it did not free up the color. So the argument as we gave it is not sufficient. So it's inverting 2 Kempe chains at once is invalid in general. It doesn't necessarily say. Oh no. Okay, so that's the catastrophe. The proof had that's the flaw. Right. So it was Haywood who noticed this flaw, and his original counterexample had 25 regions. So he found a graph of 25 regions where you try to perform the logic that we used, and it doesn't free up a color. This is a smaller example. This might be, I think this is one of the smallest possible counterexamples. So trying to keep it simple to draw. But okay, so there's problems. There are counterexamples for a reason, and I guess the intuition here, or the way you should think about this, is that in general, recoloring is difficult. Like the general case, graphs can be funky and then make it really difficult to recall. So unfortunately, the argument doesn't hold up in general. Okay, but at least we did get a 5 color here. So that proof was sound. We were able to do the recoloring. Okay, but the final proof of the four color theorem wasn't done by induction. So they didn't actually resolve this. How do you color define? That wasn't resolved. Instead, the proof of the five color theorem, so it was done by Appel and Haken in 1976, and it's notorious for being the first major proof, first proof of a major theorem that like had a heavy reliance on computers. And so this was at a time, so 1976. Okay, so I was not around, so I feel weird sort of doing this kind of historical part. But so 1976, this is before like home computers were so well, I guess what I wanted to say was that like this proof was controversial. It was controversial because people like mathematicians who didn't use computers, they weren't popularized as much. They maybe were skeptical or of this use of computer. Now, what is a computer? Mathematicians are doing. We do our work. What is this box doing? It's unfamiliar. I don't know if that's totally accurate. But the proof used computers to check a lot of cases. So I think people who know about this proof about using computers know that there's something to do with using a lot of cases. But cases of what? You can't check every graph. There are infinitely many. So somehow they had to come up with a way where they could, reduce the space of things you had to check to something finite that something reasonable to do with it. I think if we haven't gotten too long, I just want to make sure we don't take very long. But I wanted to tell you a little bit about the actual proof and what the computers are being used to do, because I think it's interesting. Can I just do a time check?
Yeah, 47.
So, okay. Yeah, let me see if I can wrap this up in about 10 minutes. Okay, yeah, so I just want to tell you a little bit about what they actually do with the computers. What were the cases? What were they checking? How does it work? What was the logic behind this proof? Because it's really nice. So let's see. Yeah, so I have a picture of since Appel and Haken, and they're looking at their cases. So this is a picture from 1976 when they proved the four column theorem. And this is a picture from their paper they wrote. I just wanted to read a little bit of what they were saying. So so they said they're saying that there's the trait restriction to only triangulations. So these are graphs where all of the shapes are triangles, like the graphs that we were drawing. The idea is that if your graph ever has a shape in it that's not a triangle, then you can make the coloring problem harder by adding an extra connection. This is harder to tell. If you're able to use if you're able to prove that this is four colorable, then so is the thing without the edge. So just removing the edge makes it easier. So there's one less constraint. So they're saying that actually it's enough to just consider the maps that where the graphs are all just made up of all triangles. So it's and they're also saying that you can only consider graphs where the lowest number of neighbors is 5. So graphs that have a neighbor, graphs where the vertex is only 4 or 3 or 2 neighbors, the induction argument works. You can use the Kempe chains, the kinds of arguments that we made exactly that you can do recoloring. So the induction works for those. So the real tricky ones are where all of the vertices are have lots of neighbors, and the least neighbored one has 5. Yeah, so there was a reduction. You just have to consider those. Okay, and then what they're actually doing is, so you say that there's a theory of unavoidable sets and reducible configurations. Yeah, so let me just tell you a little bit about this. So it says a configuration. Here. So a configuration is a subgraph consisting of a circuit, so a ring of countries, and then some of regions, and then some regions inside. here's a picture of that. I want to show you a picture on the next slide. But I also want to get this piece in here. So they also talk about a set of configurations being unavoidable, meaning that any map must have one of those configurations in it somewhere. So an unavoidable set is like this just set of things where every graph must have one of them in it. It's like features that you must have one of these features. Okay, so here's a picture of what configurations look like. So there's there's a ring of regions and then some stuff in the middle. Here it's just a single region in the middle. This is an unavoidable set. This is actually a picture version of the Euler statement. Euler's saying there must be a vertex that has at most 5 neighbors. What he's saying is there must be a country with at most 5 neighbors. So every graph is going to have a country with at most 5 neighbors. So every graph will have one of these configurations. Okay, so this is an example of an unavoidable set. Just a set of, motifs, pictures that every graph must have. Now, what they want to do is, what you want is an unavoidable set where all of these configurations are what they're calling reducible. And what reducible means is the way they're saying it. Reducible for a configuration to be reducible, it means that if you're able to, if you remove what's inside, and have a forecoloring of the rest, so of the ring, then when you put that region back, there's always a way to complete the coloring as a forecoloring. So let me say that again. So reducible means that anytime you're able to forecolor the ring, you can complete the coloring by coloring in anything inside, so that it's all the whole thing is full. That's what they call reducible. And actually, some of these are reducible. We proved using the Kempe chains that these cases are reducible. Like you might have to do some recoloring. Like the one with 4, you can do the north-south Kempe chain and the east-west Kempe chain. They can't both coexist. So that's recoloring. The Kempe. So the problem though is that Kempe couldn't show that this having 5 neighbors is always recolorable. So that's the one where our proof just did not get to. We weren't able to show in general that you can find a color for that middle vertex. I probably should put a question mark, but not reducible, maybe. Like we just haven't. No one has shown it. We weren't able to. This is another unavoidable set. This one is Vortex unavoidable set. It's just saying that every graph must have one of these pictures in it. Well, these are the double pentagon and the pentagon, hexagon. But when this was found, these 3 are reducible, but maybe these ones he wasn't able to show if these were reducible. Okay, I didn't tell you why reducibility matters. Sorry. So the idea is from Appel and Haken, they're saying is that you want to see if you can find put these ideas together and look for an unavoidable set of reducible configurations. So unavoidable set of configurations, and all of them are reducible. That's this unavoidable set reducible configurations. If you can find one of these things, you just proved the 4 color thing. Here's why. Imagine, you know what? Should I know this is not everything. I don't have like a slide for this, but just wanted to draw it. Probably not go on too long with this. But this is the core idea of their proof of the 4 color thing. Imagine that there are counterexamples to the 4 color thing. There are maps which 4 colors is not enough. Okay, so imagine there are counterexamples to the 4 color theorem. Imagine these have lots of regions, and 4 colors does not work. Okay, but you have an unavoidable set of reducible configurations. So that means that all of these, somewhere in them, have one of those reducible configurations. So let's put it in. It has a reducible configuration. All of it. Okay, so among all of the counterexamples, find the one that has the fewest regions in it. They all have some number of regions. Pick the smallest one. Because this is like a minimal counterexample with the fewest regions. Okay, so this is the smallest graph that can't be four-colored. That's going to be a problem when you pull out the middle of the reducible configuration, because when you remove this, imagine there's just a hole. You just have a graph with fewer regions. Okay, that's going to be a problem because it has fewer regions. So if it isn't four-colorable, it's now a smaller minimal counterexample. That contradicts this one was good. And if this new thing with that hole in it is four-colorable, so you're able to do a coloring of it, then because by the definition of reducible configuration, you can complete the four-coloring somehow. And then you just four-colored this counterexample. That's also a okay. So it's a total contradiction. So you found a minimal counterexample, which means that there can be no counterexamples in four-color theorems too. Okay, I rushed a little bit. This is the idea behind the proof. If you can find unavoidable set reducible configurations, there can be no counterexamples. Okay, and they found one. Here's a kind of suggestive picture from their paper. They classified them, and here there are 15. There were actually more than 15 in their set. Do you want to guess how many there were? 300. 300. It's more than 300. 600. It's more than 1,000.
So 1900s.
So 1900. Yeah, 1,936. So they were able to find an unavoidable set of reducible configurations of size 1,936, all proved to be reducible, and this whole thing is unavoidable. So every planar graph has one of them. It's amazing. So that's an accomplishment itself. So the goal was, or actually, no, that was the proof. So what took all the work was once they established an unavoidable set, they used computers to check they're reducible. So to check that something's reducible, you have to show that no matter how you color the ring, you can always complete the coloring. That's like a huge brute force. You have to try all possible colorings of the rings and make sure you can. You might not be able to color the inside directly. You might have to do recoloring with Kempe. It's really bad. But they use computers to that. These are the cases. This is what the computer was doing. It was checking all these things to be reduced. Okay, and they are. So that's a proof of the four colors. Pretty amazing. And so they were able to reduce that number down to 1,400 eventually, like 1,405. I think I don't have it written down, but people may have gotten this number down smaller. But it really doesn't matter what's the size of the set. Well, once you find one, yes, we're done. This was very exciting. So they were at the University of Illinois, and once they announced their success, the University of Illinois started using this postmark. Four colors suffice to announce to the world this they're very cool. And since then, so in 2004, they wrote not them, but there is a formally verified using like the theorem proving the computer formal language theorem proving the four color theorem is proved. They were able to translate this into like that formal language and verify it. So that maybe, I don't know if that actually helps the skeptics who didn't like the computers. Now it's like extra computer, but okay, so maybe we can feel a little bit better about it. Yeah, I was thinking about how just in general, this Kemp's argument, I wanted to share it because I think it's a good example of how sometimes pictures and intuitive reasoning can mislead you when you think you're doing some kind of a general thing, but you've actually missed a case. So that can happen when you sort of are misled by trying to be intuitive. And it just reminds me of how with AI now, sometimes you have that case where AI is like trying to be convinced. AI sounds convincing, but it's actually being misleading. Like it's making mistakes that sounds convincing. So we have to face problems like this all the time now with just like Kemp's so I guess we're like learning to be more like alert skeptical. It's probably healthy for us as mathematicians to do that. But okay, that's all. So thank you.
Questions?
So an obvious question that comes to mind when you pose a problem like this is, suppose I gave you a graph and asked you to four-color it, right? There would be an algorithm. Should be an algorithm to do that. Kemp's proof gives you a flavor for an algorithm that you could use, right? You start out coloring, and then when you hit one of these roadblocks, you find the chains and you do the inversion and you keep going. And then, at some point, maybe you can't do that anymore because you hit the subcase. Right? And so, do you know anything about actual algorithms for coloring and how they work? And
Yeah, I'm sorry, I don't. I don't know about the graph color algorithms. And whether modern ones use the kind of chain conversions.
so, you'd start to think about doing that with Kemp, and then you'd have to run into this, a graph that fails somehow, where you go and recolor, and then you try to recolor the other one, get stuck in your loop. So it would be interesting to know. I mean, Appel and Haken don't suggest to me a way of developing an algorithm that would be easy to implement.
It's funny, speaking of the algorithm, because I read something where after he sent his abstract, I just kind of looked at some of the history of it. And there was some snarky mathematician from the 1800s that had looked at in the library a bunch of old maps. He said there were a lot of these things were three colorable and they were using six colorable. He said if the four color conjecture is true, it is certainly unknown to cartographers. So I have a question also. You said it was 1936 cases. Is that right?
Yeah.
That's 44 square. Is that do you know if that's coincidence?
Oh, wow. That's amazing. I don't know. That's very cool. Yeah.
If you go back to the map of the United States.
Yes, I can go back to that. I think I can. Oops. Yeah, it's gonna pop down. There it is. Okay.
So Michigan, it's giving me like Michigan, I feel like could add problems to it if it weren't very clearly its own region. Do you know if in general there's like like how Maine used to be a part of Massachusetts in general, to maps where we have that kind of non-connected regions?
So you're saying that those two disconnected regions are forced to be colored the same?
Yeah,
Is that induce a problem?
That is such a good point. Yeah, so it is two disconnected regions. So the four color theorem would guarantee you can do this, but maybe you would have to color it differently. Once you enforce that they have to be the same color, in general, when you try to enforce coloring restrictions on a map, there may be no possible completions. So there are graphs where when you give a partial coloring, there are no continuations to make. Probably for the United States. Well, okay, actually, yes, for the United States we could do it. But in general, disconnected regions where you.
So what you do is when you convert it to a graph, those two regions become one node, and their neighbors become the neighbors of Maine become also neighbors of Massachusetts, and that may cause a planarity problem.
Oh yeah, that's interesting because like Wisconsin is a neighbor of this part of Michigan, so we'll just say it's a neighbor of Michigan. Yeah.
Other questions? Okay, let's think then again.
Point out that the original code was written in Fortran.
That's old school, baby.